Welcome to Section 20.1, Part 1. This is the 198th session of the CISSP Exam Prep series. In this session, we'll look at where security fits into custom software. We'll answer several questions. Why do homegrown applications carry so much risk? What kinds of programming languages exist? And why does that matter? How does compiled code differ from interpreted code in a security sense? What danger hides inside shared libraries and machine learning components? What tools do developers rely on? And how does object-oriented design shape security? And what does assurance really buy you? Why does this matter beyond the exam? Because you will sit in design meetings where developers make choices that quietly set the security posture for years. Picture a logistics firm writing its own route planning app. If a careless engineer leaves a backdoor or a sloppy input path, that flaw ships to every warehouse. Knowing how software is built lets you spot these risks before they harden into production. So, why do custom-built applications carry so much risk? Because organizations write their own software to serve goals, no vendor product covers, and that code is only as safe as the people who write it. A rushed or malicious developer can plant a hidden backdoor, leave a buffer overflow, or forget a check that lets an outsider in. The fix is to weave security controls through the entire development lifecycle rather than bolting them on later. Think of building a house. Wiring and plumbing are far cheaper to route correctly while the walls are open than to tear open finished drywall afterward. Why build security in from the very first stage? Because retrofitting protection into a finished system is slow, costly, and leaky. Every application deserves security proportional to how sensitive its data is and how critical its job is. A payroll engine handling salaries needs far tighter guarding than an internal lunch menu page. Decide the security posture while the design is still fluid, and the whole structure bends to accommodate it. What kinds of programming languages do developers actually use? At the bottom sits machine language. The raw ones and zeros a specific processor understands, which almost no human reads directly. One step up is assembly language, which swaps those numbers for short mnemonics, but still demands deep hardware knowledge and endless lines for simple tasks. Above that live high-level languages like Python, Java, and C#, which read closer to human instructions, speed up development, and travel more easily across platforms. Think of it as the difference between speaking in Morse code, in shorthand abbreviations, or in plain sentences. How does a program actually get from source code to running software? Two paths exist: compilation and interpretation. A compiled language uses a compiler to translate the human-readable source into an executable file built for one operating system, and that finished file is what you hand to users. Normally, nobody can read the original instructions inside it, but reverse engineering specialists use decompilers and disassemblers to work backward towards source or assembly, which is handy for malware analysis. Obfuscation deliberately scrambles an executable to slow those tools down. Some languages instead lean on a runtime, like the Java virtual machine, that users install so the same compiled code runs anywhere. How does interpreted code differ? And what does that mean for security? With an interpreted language such as Python or JavaScript, you ship the source code itself, and an interpreter on the user's machine runs it line by line. Because the source travels in the open, anyone can read it. That cuts both ways. Compiled code resists outside tampering, but a dishonest developer can bury a backdoor no end user will ever see. Interpreted code exposes that hidden logic to inspection, yet everyone who touches the file can also alter it. Picture a sealed appliance versus a recipe card. One hides its inner workings, the other invites both review and meddling. Why are shared libraries both a gift and a hazard? Developers reuse pre-written libraries so they never rebuild common functions like sorting or text handling from scratch, which saves enormous effort. The catch is that a flaw in a popular library spreads to everything that includes it, often silently. A famous flaw in a widely used encryption library forced administrators across the globe to scramble because countless products had bundled it without users realizing. So track where your borrowed code comes from and watch for newly disclosed weaknesses in it. The same discipline now extends to machine learning, where pulling a pre-trained model or dataset from an untrusted source can smuggle in hidden backdoors or poison behavior. What tools and design styles shape how developers work? The central tool is the integrated development environment, a single workspace where a programmer writes, tests, debugs, and compiles code together. On the design side, object-oriented programming models a system as a collection of objects that pass messages and perform actions. A banking program, for instance, might have objects for accounts, account holders, and employees, each carrying methods like adding funds or closing an account. Objects can inherit behavior from a parent class, so a checking object gains everything an account has plus its own extras. From a security angle, this gives you a black box style of abstraction. Each object is encapsulated and self-contained, reachable only through defined messages, so a user works the interface without touching the fragile internals. What do the core object-oriented terms mean in practice? A message is the input sent to an object, and a method is the internal code that runs in response. The observable result is the behavior. A class is the shared blueprint of methods, and each object is an instance built from that blueprint. Inheritance passes methods from a parent class down to a child, while delegation hands off a request an object cannot handle itself. Polymorphism lets one object answer the same message differently as conditions change. Two quality measures round it out. High cohesion means a class's methods share a clear common purpose, which is good design. Low coupling means objects depend little on each other, which makes them easier to fix and update. What does assurance actually give you? Assurance is the formalized process of building trust into a system's whole life cycle, confirming that the security mechanisms you designed keep enforcing the policy over time. It is not a single test, but an ongoing confidence that the controls do what they claim. In government settings, a standardized approach called the Common Criteria provides a shared yardstick for measuring that trust. Think of it as an inspection regime, not a one-time stamp that keeps vouching for the system as it ages. So let's bring it together. Custom software carries real risk, so you build security in from the first design stage rather than patching it on later. Languages range from raw machine code up to high-level tongues, and the compile or interpret choice trades tamper resistance against transparency. Shared libraries and machine learning components inherit any hidden flaws, so you vet their origins. Integrated environments and object-oriented design shape both productivity and protection, and assurance keeps confirming the controls hold over the system's life. Master these foundations, and the rest of the development story fits neatly on top. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.1, Part 2. This is the 199th session of the CISSP Exam Prep series. This part shifts from language choices to the practical safeguards that keep running software from failing dangerously. In this session, we'll examine how to keep applications resilient and how to structure their development. We'll answer several questions. How do you stop bad input from breaking a program? How should applications handle authentication and sessions? What do error messages and logs reveal, and to whom? When software fails, should it lock down or open up? And how does a formal life cycle guide the earliest phases of a build? Why does this matter beyond the exam? Because the difference between a minor glitch and a full breach often comes down to these unglamorous choices. Imagine a hospital's appointment portal that a patient can reach from any browser. If it trusts whatever text arrives or spills its database layout in an error page, an attacker gets a roadmap. Getting input handling, failure behavior, and phase discipline right is what keeps that portal boring instead of newsworthy. How do you stop bad input from breaking a program? You validate it. Input validation checks that whatever a user submits matches what the code expects before anything acts on it. If a field asks for a month, the program should insist on a whole number from 1 to 12, a rule called a limit check, and politely reject anything else. It also scans for suspicious characters that hint at an attack, and it can neutralize risky sequences by escaping them, swapping dangerous symbols for harmless stand-ins that display the same but never execute. The one rule you never break is to validate on the server, because anything running in the user's browser can be tampered with and slipped past. Think of a bouncer who checks every guest at the door, not one who trusts the guest list they were handed. How should applications handle authentication and sessions? Match the strength of the login to the sensitivity of what lies behind it. An application holding sensitive data or letting users run critical operations deserves strong multi-factor authentication, not just a password. Wherever possible, plug into the organization's existing hardened identity system rather than inventing your own. And if you truly must build one, lean on externally vetted authentication libraries. Sessions need the same care. Any cookie that tracks a session should travel only over encrypted channels, carry a long random identifier, and expire after a set time so users must sign in again. Picture a wristband at an event that is hard to forge, tied to one person, and stops working once the show ends. What do error messages reveal? And to whom? Developers love verbose errors because they make debugging painless. But those same messages can hand an attacker the internal map. A detailed error can leak database table names, internal server addresses, and other reconnaissance gold. So on anything publicly reachable, switch off detailed error output, often called debugging mode, and show users only a bland, safe message. The valuable details should not vanish, though. It belongs in logs. What should you log, and why does it matter? The rich information that would endanger a user-facing error page is exactly what your security team needs behind the scenes. Send detailed records of errors and security events to a central log repository where analysts can study them. Capture the events that tell a story of trouble, like failed input validation, authentication attempts and especially failures, access control denials, tampering with saved state, use of expired session tokens, system exceptions, administrative and security setting changes, and cryptographic or secure channel failures. Together, these give you the trail to diagnose issues and investigate incidents. Think of a store's security cameras. You do not broadcast the feed on the storefront, but you keep it recorded for when something goes wrong. When software fails, should it lock down or open up? You must decide this in advance, because failures are unpredictable and code will get used in ways nobody imagined. A fail-secure state throws the system into a high-security posture or shuts it down entirely until an administrator can investigate and restore it. A fail-open state does the opposite, letting users slip past the broken control and erring toward permissiveness. In almost every environment, fail-secure is the right default because it blocks unauthorized access when things go wrong. The blue crash screen on a desktop operating system is a familiar example. When the system detects that its environment is no longer trustworthy, it halts rather than keep running in an unreliable, insecure state. What happens after a fail-secure event, and when is fail-open ever acceptable? Once a system safely stops, you choose whether it stays halted for a human to review or reboots itself automatically. Staying down forces an administrator to step in, which you can enforce with a boot password. Automatic recovery needs no human, but it must reboot into a restricted state, never auto-logging in and always prompting for credentials. Fail-open is a rare exception, sometimes justified for a lower layer of a multi-layered defense, and only after you clearly validate the business need and back it with alternative controls. Remember too that ship security is often switched off for easy installation, so administrators must deliberately turn it on. Every notch of added security tends to cost more, add overhead, and trim convenience, so you are always balancing protection against usability. How does a formal lifecycle guide a build? Security works best when it is planned and managed across the system's entire life, and project management keeps that effort on track. Formal lifecycle models embed good practice and security into every stage, instead of leaving it to chance. Whatever the model, the same core activities recur. You define the concept, determine functional requirements, develop control specifications, review the design, write the code, walk through code reviews, run system testing, and then maintain and manage change. Do not obsess over the exact labels, which shift from one text to another. Grasp how the flow works. Think of it as a recipe with named steps. Different cookbooks phrase them differently, but the sequence of preparation stays the same. What happens in the conceptual definition phase? You write a short concept statement, agreed by every stakeholder, developers, customers, and management alike, that captures the project's purpose and its broad requirements. Keep it to a paragraph or two, high enough that an outsider grasps the whole aim in a glance, like the abstract at the top of a report. The security requirements here stay very high level and get refined later, But this is where you flag what classes of data the system will handle and their handling rules. Reread the concept statement throughout the project, because the daily detail has a way of hiding the overarching goal. What happens during functional requirements determination? Once everyone agrees on the concept, the team spells out exactly what the system must do and how its parts should work together. The deliverable is a functional requirements document written in a form developers can build from. Each requirement rests on three characteristics: the inputs, meaning the data a function receives; the behavior, meaning the business logic that decides how the system reacts to those inputs; and the outputs, meaning the data the function hands back. Get every stakeholder to sign off before moving on, then keep the document alive as a constant reference and, at the end, as the checklist that confirms every requirement was met. Think of it as the blueprint the whole build measures itself against. Why give control specifications their own phase? Because security designed in from the start integrates cleanly, while security bolted on later leaves gaps. This phase, sitting just after functional requirements and running into design, is where you analyze the system through a security lens. You build in access controls, so only authorized users get in and none exceed their permissions. You protect confidential data with appropriate encryption. You provide an audit trail for individual accountability and a way to detect illegitimate activity. And for critical systems, you address availability and fault tolerance. Revisit these requirements every time the design changes significantly, because a major component shift usually shifts the security needs with it. Retrofitting security is like adding a fire escape to a finished tower. It never fits as well as one planned into the frame. What happens at design review? With functional and control specifications settled, the designers work out exactly how the pieces interoperate and how the modular structure lays out, while management assigns tasks and sets coding timelines. When the formal design documents are done, the stakeholders meet to confirm everyone still agrees the project is on track to deliver the intended functionality. Crucially, security professionals belong in that room, validating that the proposed design honors the control specifications set earlier. Think of it as a dress rehearsal review before the cameras roll, catching mismatches while they are still cheap to fix. So let's bring it together. Validate every input on the server and match authentication and session handling to the sensitivity of what you protect. Hide detailed errors from users, but log them centrally for your analysts. Default to fail secure so trouble locks things down, and treat fail open as a rare, justified exception. Then structure the build with a formal life cycle, moving through concept, functional requirements, control specifications, and design review, weaving security in at each step. Master these habits, and resilient software becomes the default rather than the exception. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.1, Part 3. This is the 200th session of the CISSP Exam Prep series. This part carries the build forward from writing code through testing, maintenance, and the major lifecycle models. In this session, we'll walk the middle and later stretches of development and the models that shape them. We'll answer several questions. What happens once coding begins, and how is it reviewed? How do you test a system before it goes live? Why does change management never really end? And what do the classic lifecycle models, from waterfall to agile at enterprise scale, actually give you? Why does this matter beyond the exam? Because the model your teams follow decides how quickly flaws surface and how safely fixes ship. Picture a fintech startup racing to launch a payments feature. If they skip code reviews and structured testing, a single mishandled edge case can move real money the wrong way. Understanding these phases and models lets you insist that security rides along at every stage instead of getting left at the platform. What happens once coding begins, and how is it reviewed? Once stakeholders bless the design, developers start writing code that matches the agreed plan and applies secure coding principles. Because fresh code always hides mistakes, project managers schedule code review walkthroughs at coding milestones. In these technical sessions, developers sit down with a specific module and step through it line by line, hunting for logic errors and security flaws. Only development staff usually attend, and the goal is to confirm each team's code behaves as specified. Think of it as proofreading a manuscript chapter by chapter before it ever reaches the printer. How do you test a system before it goes live? Testing starts inside the team, with developers hunting obvious errors, then widens as developers and real users run the system against scripted scenarios covering both ordinary and unusual activity. When you are updating an existing system, regression testing confirms the new code behaves like the old, except for the changes you intended. Cover both functional testing, which proves the software works, and security testing, which proves no serious weaknesses slip through. When everyone is satisfied, users perform acceptance testing, formally agreeing the software meets their needs and is ready for production. Keep the written test plan and results as permanent records. Think of it as a test drive on a closed course before the car is ever sold. Why does change management never really end? Because the moment a system goes live, its maintenance begins and never stops. Operational needs, data volumes, storage, and the surrounding environment all keep shifting. So you need a skilled support team ready for both routine and surprise upkeep. Every change to the code must flow through a formal change management process rather than happening ad hoc, so nothing slips in unreviewed. Think of it like maintaining a bridge. It carries traffic for decades, but only because crews inspect and repair it on a disciplined schedule. What do lifecycle models actually give you? They bring engineering discipline to what can otherwise be chaotic. Improvised coding. Having a management model in place tends to produce better products. But a poor or ill-fitting model can steer a project away from real business needs, so verify that the model suits your environment and win management approval up front. Choosing the model is usually the development team's job, and your role as a security professional is to make sure security principles are woven into whatever model they pick. Think of it as choosing a construction method. The right one for a house differs from the right one for a skyscraper, but every method needs safety built in. How does the waterfall model work? Waterfall views development as a series of sequential stages, each completed before the next begins, flowing steadily downward like water over a ledge. The purely linear original proved too rigid, so the iterative version added feedback loops that let a project step back to the previous phase to fix defects discovered later. A further refinement, the modified waterfall, added verification and validation at each phase, where verification checks the product against its specifications, and validation checks how well it meets real-world needs. Its main weakness is that it lets you step back only one phase, so a fault found much later is hard to unwind. Think of it as an assembly line that can nudge a part back one station, but no further. How does the spiral model improve on that? The spiral model wraps several passes of a waterfall-style process into repeated loops, which is why it is called a model of models. Each loop produces a new prototype, and developers keep circling through planning, building, and evaluating, incrementally maturing the system while resolving risks each time around. This solves waterfall's big limitation, because you can return to the planning stages whenever changing technology or customer needs demand it. Where waterfall aims for one large finished delivery, spiral iterates through steadily more complete prototypes with tighter quality control. Think of it as sculpting through repeated rough drafts, each one closer to the final form. What makes the Agile approach different, and how does Scrum apply it? Agile grew from a reaction against rigid, heavyweight models, valuing individuals and interactions, working software, customer collaboration, and responding to change. It is a philosophy, not a single method, and several methodologies put it into practice, with Scrum the most popular. Scrum runs on short daily meetings, also called scrums, where the team reviews progress, plans the next day, and clears obstacles, guided by a Scrum Master who keeps things moving. Work happens in sprints, tight windows usually of 1 to 4 weeks, each ending in a functioning, releasable product that grows richer sprint by sprint. Think of it as building a working car one drivable version at a time, rather than unveiling the finished vehicle only at the very end. What is an integrated product team? The idea of gathering all the right stakeholders around one product goal is older than Agile itself. A defense organization introduced integrated product teams as multifunctional groups sharing a single aim, whether delivering a product or shaping a process or policy. Their purpose was to foster parallel rather than sequential decisions, so that every angle of the product, process, or policy gets considered throughout development instead of in isolation. Think of it as seating design, security, and operations at the same table from day one, rather than passing a document down a hallway. How does the scaled Agile framework stretch Agile to the enterprise? Large organizations struggle to run Agile across many teams at once, and the scaled Agile framework offers a structured way to coordinate hundreds or even thousands of practitioners. At its heart, it gives everyone a shared picture of how work flows from team-level activity up to strategic goals. It is organized into 4 configuration levels. Essential brings in core Agile practices, with teams grouped into release trains that deliver larger increments of value together. Large Solution adds coordination for enormous systems that need multiple trains. Portfolio translates strategy into funded, actionable work under lean management principles. And Full combines all of these for the biggest, most integrated efforts. It ties every task, from broad themes down to individual stories, back to a larger objective. Think of it as scaling a single kitchen's rhythm up to run an entire restaurant chain in sync. So let's bring it together. Coding follows an approved design and gets checked through line-by-line walkthroughs. Then testing moves from developers to users, adds regression checks, and ends in formal acceptance. Change management runs for the life of the system, always through a formal process. Lifecycle models bring discipline. From sequential waterfall, to iterative spiral prototypes, to flexible, agile, and its Scrum practice, up to the scaled Agile framework for enterprise scale. With integrated product teams as an early collaborative ancestor, master these, and you can insist security travels through every phase and every model. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.1, Part 4. This is the 201st session of the CISSP Exam Prep series. This part turns to maturity models, project scheduling, and the disciplines that keep changing software under control. In this session, we'll measure how organizations mature and how they govern change. We'll answer several questions. What principles guide Agile at scale? How do maturity models chart the road from chaos to discipline? What tools help you schedule and size a project? How do change and configuration management keep production safe? And how do the modern DevOps and DevSecOps approaches fold everything together? Why does this matter beyond the exam? Because these frameworks are how leadership judges whether a software shop can be trusted with critical work. Imagine an insurer evaluating a vendor to build its claims platform. Knowing where that vendor sits on a maturity ladder and how tightly it controls changes tells you far more about risk than any sales pitch. These are the yardsticks you will use to hold both internal teams and outside partners to account. What principles guide Agile at scale? The Scaled Agile framework rests on a set of core principles drawn from Agile thinking, and together they steer how large organizations make decisions. They urge you to take an economic view of every choice and to apply systems thinking to the whole. They tell you to assume variability and keep options open, build incrementally with fast learning cycles, and base milestones on objective evaluation of working systems. They push you to make value flow without interruption, apply a steady cadence synchronized across domains, and unlock the intrinsic motivation of your knowledge workers. Finally, they ask you to decentralize decision-making and organize everything around value. Think of them as the shared rules of the road that let a huge convoy of teams drive in the same direction without constant collisions. How does the capability maturity model chart the road from chaos to discipline? This model holds that every software organization climbs through the same 5 stages in order, from disorganized effort toward mature, repeatable practice, on the premise that software quality follows process quality. At level 1, initial, hardworking people push ahead with little defined process. At level 2, repeatable, basic lifecycle management and organized code reuse appear. At level 3, defined, teams work from formal, documented, standardized processes. At level 4, managed, quantitative measures give a detailed grip on the process. And at level 5, optimizing, continuous improvement feeds lessons back to refine future work. A successor model integrates these once isolated processes rather than treating them separately. Note that the model itself does not address security, so weaving security in is on you. Think of it as a fitness ladder, climbing from random workouts to a measured, self-correcting regimen. What does the software assurance maturity model add? This open source model exists specifically to fold security into the development and maintenance process, and it lets an organization assess its own maturity. It divides the work into 5 business functions. Governance covers how you manage the process, including strategy, metrics, policy, compliance, and education. Design covers defining requirements and shaping the software, including threat modeling and security architecture. Implementation covers building and deploying components and handling their defects. Verification covers confirming that code meets both business and security requirements through assessment and testing. And operations covers keeping confidentiality, integrity, and availability intact after release through incident and environment management. Think of it as a security-focused report card with 5 subjects, each graded on how mature your practices are. What does the ideal model contribute? The ideal model organizes improvement into 5 phases that mirror the maturity mindset. Initiating lays out the business reasons for change, builds support, and sets up the groundwork. Diagnosing analyzes where the organization stands today and recommends broad changes. Establishing turns those broad recommendations into a specific action plan. Acting develops, tests, refines, and implements the actual solutions. And learning reviews whether the goals were met and proposes new actions to stay on course. Think of it as steering a ship. You set out, take your bearings, chart a route, sail it, and then check the stars to correct your heading for the next leg. What tools help you schedule and size a project? 2 classics show up here. A Gantt chart is a bar chart that maps tasks against time, showing how projects and schedules interrelate, which makes it ideal for coordinating work that shares the same people or resources. The program evaluation review technique, by contrast, helps you judge the size of a software product and gauge risk by combining the smallest likely size, the most likely size, and the largest likely size of each piece, while laying bare the dependencies between tasks. Together, they let managers plan timing, track progress, and schedule around bottlenecks. Think of a Gantt chart as the calendar view and the review technique as the estimate that tells you how big each block on that calendar really is. How does change management keep production safe? Once software is live, users will always want new features, bug fixes, and tweaks, so you manage those changes in an organized way and log them to a central repository for auditing and investigation. The process has 3 parts. Request control gives users a framework to ask for changes, while managers weigh costs and benefits and developers set priorities. Change control lets developers reproduce the reported situation, craft and test a fix in a controlled setting, document it, and limit its side effects on security. Release control approves the finished change for production, and its essential job is to confirm that any debugging code or backdoor added as a temporary aid gets stripped out before shipping. Think of it as an airlock. Nothing reaches the live environment until it passes through each sealed, checked stage. What does software configuration management control? Alongside change management, configuration management governs which versions of software run across the organization and formally tracks changes to that configuration. It has 4 components. Configuration identification documents the configuration of the covered software products throughout the organization. Configuration control ensures version changes follow the change control and configuration policies, allowing updates only from authorized sources. Configuration status accounting keeps formal records of every authorized change. And configuration audit periodically checks that the real production environment matches those records and that no unauthorized changes crept in. Think of it as an inventory system for software versions, one that not only records what should be running, but regularly verifies that reality agrees. How does the DevOps approach fold everything together? For years, software development, quality assurance, and operations sat in separate silos that often clashed, throwing problems over the fence and delaying releases. DevOps merges these three functions into one cooperative model, and its very name fuses development and operations to signal that they must work as one. Closely tied to Agile, it slashes the time to develop, test, and deploy, so that organizations which once shipped major releases yearly can push code many times a day. Think of it as tearing down the walls between three departments so a single team owns a change from idea to production. How do DevSecOps and continuous delivery complete the picture? When code moves fast, security has to move just as fast. So many teams prefer the term DevSecOps to signal that security joins development and operations as an equal partner. This approach supports software-defined security, where controls are managed by code and dropped straight into the pipeline. That pipeline is continuous integration and continuous delivery, a highly automated flow that ties together code repositories, configuration management, and the movement of code between development, testing, and production, letting some organizations roll out changes dozens or hundreds of times a day. Think of it as an automated assembly line where safety inspections are built into the conveyor itself, not tacked on at the end. So let's bring it together. Scaled Agile rests on core principles that align huge organizations around value and flow. Maturity models chart the climb from chaos to discipline, with the capability maturity model measuring process, the assurance model folding in security, and the ideal model guiding improvement. Gantt charts and the review technique schedule and size the work. Change and configuration management keep production trustworthy, and DevOps with DevSecOps merges development, security, and operations into one fast, automated pipeline. Master these, and you can measure and govern software work with confidence. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.1, Part 5. This is the 202nd session of the CISSP Exam Prep series. This part closes our tour of development controls with interfaces, testing, repositories, and acquired software. In this session, we'll cover how software talks to other software and how you verify and source it safely. We'll answer several questions. What security do application interfaces demand? How do you test software thoroughly and fairly? What testing philosophies can you choose from? How do code repositories help and endanger you? What do service agreements guarantee? And what changes when you buy software instead of building it? Why does this matter beyond the exam? Because modern systems are stitched together from many services and outside components, and each seam is a potential weak point. Picture an online retailer that leans on an outside payment service, a shipping integration, and a pile of open source code. Every interface, test gap, or exposed secret is a doorway. Knowing how to secure interfaces, test rigorously, guard repositories, and vet purchase software is what keeps that whole quilt from unraveling. What security do application interfaces demand? Modern web applications constantly talk to other services, and application programming interfaces let developers skip the web page and call the underlying service directly through defined functions. That power carries risk. So the first question is authentication. Some interfaces, like a public weather lookup, need none. But any interface that changes data, places orders, or exposes sensitive information must verify credentials and authorization on every single call. This is usually done with a complex API key passed along with each request, which the backend validates before acting. Treat that key like a password, storing it securely and sending it only over encrypted channels, because anyone who steals it can act as you. Tools like curl let developers post requests straight to an interface for testing, and attackers use the very same technique to probe it. Think of an API key as the badge that opens a staff door. Lose it, and a stranger walks right in wearing your identity. How do you test software thoroughly and fairly? Test everything before it ships, because testing is central to finding and mitigating risk. Design your tests as you design the modules, building datasets that exercise every path with known correct answers ready. Run a reasonableness check to confirm results fall within sensible bounds. So a routine that reports a human weighing 600 pounds fails immediately. Probe normal input, wrong types, out-of-range values, and edge conditions, using both use cases that mirror ordinary activity and misuse cases that model an attacker. Never test with live production data early on, since a flaw could expose or corrupt it. And apply separation of duties by having someone other than the original programmer test the code, because a third party gives a broader, less biased examination than the author ever could. Think of it like proofreading. The writer skims past their own typos, while a fresh set of eyes catches them. What testing philosophies can you choose from? 3 approaches sit on a spectrum defined by how much of the internals the tester can see. White box testing examines the internal logic directly, stepping through the source code line by line to find errors, so the tester has full access to the code. Black box testing works purely from the outside, feeding varied inputs and checking outputs with no view of the internal code, which is how final acceptance testing typically runs. Grey box testing blends the two, examining the software from a user's perspective, while also using the source code to design smarter tests without analyzing the inner workings during the test itself. Think of inspecting a car. White box opens the hood, black box just drives it, and grey box glances at the manual before taking it for a spin. How do code repositories help and endanger you? Software development is a team sport, often with developers scattered across the globe working on different parts at once, and code repositories give them a shared home. Beyond central storage for source code, they add version control, bug tracking, release management, and communication features, and they integrate tightly with popular code management tools. But that convenience carries risk, and the first is access control. Some repositories are public by design, while others hold trade secrets and must stay locked to authorized developers. Grant read access too loosely, and outsiders can pull sensitive information. Grant write access too loosely, and they can tamper with the code itself. Think of a repository as a shared workshop. It only works if the right people hold keys to the right rooms. Why is leaking secrets into a repository so dangerous? Because a repository is only as safe as what developers put into it, and secrets do not belong there. The classic mistake is embedding an interface key, which is especially damaging with cloud providers, where a key can spin up servers and charge a real credit card. Push code containing such a key to a public repository, and anyone in the world can grab it, provision massive resources, and bill them to you. Worse, automated bots constantly scan public repositories for exposed keys and can pounce within seconds, long before the developer notices. The same caution applies to passwords, internal server names, and database names. Think of it as leaving your house key taped to the front door. It is only a matter of time before the wrong person tries it. What do service agreements guarantee? A service level agreement sets the level of service a provider commits to deliver, agreed by both sides, and it is wise to put one in place for any data circuit, application, database, or other component vital to staying in business. These agreements spell out concrete metrics, like system uptime as a percentage, maximum consecutive downtime, peak and average load, who handles diagnostics, and how quickly failover happens. They usually carry financial remedies too, so a provider who breaches the agreement, say by leaving a critical circuit down too long, might have to waive charges. Both sides monitor the metrics to confirm compliance. Think of it as a warranty with teeth, spelling out exactly what you were promised and what it costs the provider to fall short. What changes when you buy software instead of building it? Most enterprise software is purchased, not written in-house, and it comes in several forms. Commercial off-the-shelf software runs on servers you manage. Software as a service is delivered over the internet through a browser with the vendor running it. And open source software is built by communities and freely available, often embedded inside commercial packages. The security responsibility shifts with each. When you install and configure software yourself, your team must understand its secure configuration and stay on top of patches. In a software as a service model, most responsibility rests with the vendor, but you are not off the hook, taking on the job of monitoring their security through audits and assessments, and often retaining legal compliance duties. Whatever the source, always test acquired software for vulnerabilities, whether through your own testing, vendor results, or independent third parties. Think of it as buying a pre-built appliance. Someone else did the wiring, but you still check that it is safe before you plug it into your home. So let's bring it together. Application interfaces need authentication and carefully guarded keys on every sensitive call. Test software thoroughly and fairly, with reasonableness checks, misuse cases, no live data early, and an independent tester choosing among white, black, and grey box philosophies. Code repositories power collaboration but demand tight access control and zero embedded secrets. Service agreements pin down measurable guarantees. And acquired software shifts responsibility yet always earns a security test. Master these, and every seam where your software meets the outside world becomes a controlled one. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.2, Part 1. This is the 203rd session of the CISSP Exam Prep series. In this session, we'll build a working picture of how databases are organized. We'll answer several questions. What database architectures exist beyond the familiar relational one? How is a relational database actually structured? What are keys, and how do they tie tables together? How does the query language shape security, and what guarantees keep transactions trustworthy? Why does this matter beyond the exam? Because databases hold the very information attackers want most, from customer records to trade secrets. Picture a subscription streaming service. Its database knows every member's payment card, viewing history, and home address. If you cannot reason about how that data is structured and joined, you cannot judge who can reach what, or spot where a clever query might reveal more than intended. Understanding the architecture is the groundwork for protecting it. What database architectures exist beyond the familiar relational one? Most modern systems are relational, but two other models matter. A hierarchical model arranges records in a logical tree, giving a one-to-many structure where each node has many possible children but only a single parent. Much like a corporate org chart where one manager oversees many staff but each employee reports to just one boss. It suits naturally nested data, like the biological classification of species. A distributed model instead spreads data across several databases that are logically linked. So users see one seamless entity even though it spans many network parts. Because each field can have many parents and many children, its relationship pattern is many to many. Think of the hierarchical model as a family tree and the distributed model as a network of connected libraries that feel like a single catalog. How is a relational database actually structured? A relational database is built from flat, two-dimensional tables of rows and columns, each table looking much like a spreadsheet. The table itself, also called a relation, is the core building block and holds a set of related records. Each column is an attribute or field, such as company name or zip code, and each row is a record, also called a tuple, holding one entity's data. Two measurements describe a table. Cardinality is the number of rows, which changes often as records come and go. Degree is the number of columns, which changes rarely and usually needs an administrator. The domain of an attribute is simply the set of values it is allowed to hold. Some systems even blend relational tables with object-oriented programming to ease code, reuse, and maintenance. Think of a table as a contact spreadsheet, where each row is a person and each column is one fact about them. What are keys, and how do they tie tables together? Keys are subsets of a table's fields used to uniquely identify records and to join tables when you cross-reference data. And four types matter. A candidate key is any set of attributes that can uniquely identify a record. And a table may have several. The primary key is the one candidate key chosen to identify records, and the system enforces its uniqueness by refusing duplicates. Any candidate key not chosen becomes an alternate key. A foreign key lives in one table but points to the primary key of another, enforcing what is called referential integrity, which guarantees that the reference always matches a record that truly exists. Think of a primary key as a person's unique identification number, and a foreign key as a note on someone else's file pointing back to that exact number. How does the query language shape security? Every relational database speaks a common, structured query language, giving users a consistent way to store, retrieve, and modify data and to administer the system. Its standout security feature is granularity of authorization, meaning you can set permissions at a very fine level, limiting access by table, by row, by column, or even by an individual cell. The language splits into two parts. A data definition portion creates and changes the database's structure or schema, while a data manipulation portion works with the data inside that schema. Developers also refine table organization through normalization, a set of standard forms that reduce redundancy and misplaced data. Think of granularity of authorization as a keycard system that can unlock an entire building, a single floor, one room, or just one drawer. What guarantees keep transactions trustworthy? A transaction is a group of instructions that must all succeed or all fail together, never part way. Picture a bank transfer that adds money to one account and subtracts it from another. If only half ran, money would appear or vanish from thin air, so the two steps ride as one transaction. A completed transaction is committed and cannot be undone, while a failed one is rolled back, restoring the database to its state before the transaction began. 4 required properties, together called the ACID model, make this reliable. Atomicity means all or nothing. Consistency means the database obeys its rules before and after. Isolation means concurrent transactions do not interfere with each other. And durability means once committed, the result survives, protected by mechanisms like transaction logs. Think of a transaction as a 2-part handshake that either completes fully or never counts at all. So, let's bring it together. Beyond the dominant relational model, hierarchical databases form one-to-many trees, and distributed databases form many-to-many networks. A relational database is tables of rows and columns measured by cardinality and degree, with keys tying tables together and foreign keys enforcing referential integrity. The structured query language offers fine-grained authorization down to a single cell, and the ACID properties keep transactions atomic, consistent, isolated, and durable. Master this structure, and every database security control you meet next has a clear place to attach. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to Section 20.2, Part 2. This is the 204th session of the CISSP Exam Prep series. This part turns to the security threats and controls that live inside databases themselves. In this session, we'll examine how databases defend the data they hold. We'll answer several questions. How do you secure a database holding many classification levels? How does concurrency protect data during simultaneous edits? What are aggregation and inference attacks? What granular controls tighten access? How do you defend against those clever deductions? And what do connectivity layers and non-relational databases change? Why does this matter beyond the exam? Because attacks on databases rarely look like break-ins. They often look like ordinary, authorized queries that quietly add up to something forbidden. Imagine a government payroll system where a clerk can see totals, but not individual salaries. The real danger is not a stolen password. It is the clerk deducing one person's pay from a series of legitimate lookups. Knowing these subtle threats lets you close doors an attacker would otherwise walk through in plain sight. How do you secure a database holding many classification levels? A multi-level security database stores information at several classification levels and must check each user's clearance before returning only what they are cleared to see. The central danger is database contamination, where data of different classifications or need-to-know requirements gets mixed together improperly. To add multi-level protection to a legacy or weak database, administrators often place a trusted front end between users and the system. Another elegant tool is the database view, a stored query that presents data as if it were its own table, letting you collate, aggregate, or restrict what each user sees without handing over the raw tables. Think of a view as a stencil laid over a document, exposing only the words a given reader is allowed to see. How does concurrency protect data during simultaneous edits? Concurrency, also called edit control, is a preventive mechanism that keeps stored data correct when multiple processes touch it at once. Without it, 2 problems appear. A lost update happens when 2 processes update the database unaware of each other, so a warehouse count that should rise by 2 rises by only 1. A dirty read happens when one process reads a record from a transaction that never successfully committed, leaving it working with half-written data. Concurrency solves this with a lock that lets one user change data while blocking others, then an unlock that restores access once the change is done. Paired with auditing, it can even become a detection control by tracking changes. Think of it as one editor checking out a shared document so no one else can overwrite their work mid-edit. What is an aggregation attack? The query language offers functions that combine records to produce summary information, a process called aggregation, and it carries a hidden risk. An aggregation attack gathers many low-value or low-sensitivity facts and combines them into something of higher value or sensitivity. Consider a records clerk authorized to update where individual soldiers are stationed. Each single transfer seems harmless, but with access to aggregate functions, the clerk could count the troops at every base worldwide, force levels that are closely guarded secrets. So control access to aggregate functions tightly and weigh what they might reveal. Combining defense in depth, need to know, and least privilege blunts these attacks. Think of it as individual puzzle pieces that mean nothing alone but reveal a sensitive picture once assembled. What is an inference attack? Inference resembles aggregation, but relies on human deduction rather than raw computing power, combining non-sensitive pieces to conclude something classified. Picture an accounting clerk allowed to see total salary figures for any past date, and also the hiring dates of employees, but never individual salaries. If exactly one person was hired on a certain date, the clerk can compare the salary total from that day against the day before and deduce that person's exact pay. The defenses are constant vigilance over permissions, deliberately blurring data, such as rounding salaries to the nearest large amount and partitioning the database. Think of it as reading between the lines, where two innocent facts placed side by side quietly reveal a third that was meant to stay hidden. What granular controls tighten database access? Databases offer several fine-grained mechanisms. Semantic integrity ensures user actions never break structural rules, keeping data within valid ranges and honoring uniqueness constraints. Time and date stamps preserve integrity in distributed systems, applying replicated changes in correct chronological order across every copy. Content-dependent access control decides access based on the actual contents of the object being reached, which is precise but adds processing overhead. Cell suppression hides individual fields or cells or wraps extra restrictions around them. And context-dependent access control looks at the bigger picture, judging how each element relates to the overall activity, since a single element that looks innocent alone may prove telling in context. Think of these as adjustable lenses, each narrowing exactly what a user can bring into focus. How do you defend against aggregation and inference more structurally? Beyond watching permissions, several architectural defenses help. Database partitioning splits one database into multiple parts, each with its own distinct security level or content type, so no single view exposes too much. Polyinstantiation lets two rows share the same apparent primary key while holding different data for different clearance levels. Imagine a ship whose true, classified location is stored for cleared users, while a decoy record shows a routine patrol to everyone else, so a lower cleared user never notices anything was hidden. It costs extra storage but foils inference. Finally, noise and perturbation inserts false or misleading data to thwart confidentiality attacks, though you must apply it carefully so it never corrupts real operations. Think of these as compartments, decoys, and smoke, each designed to keep an observer from assembling the true picture. What does a connectivity layer like Open Database Connectivity change? Open Database Connectivity lets applications talk to many different kinds of databases without being programmed specifically for each one. It sits as a proxy between the application and the back-end database drivers, freeing developers to build solutions without worrying about which database engine sits behind them. Think of it as a universal travel adapter, letting one plug work in outlets of every shape without rewiring the appliance. What do non-relational databases change? As data grows and stops fitting neatly into tables, many organizations turn to non-relational databases, which use models other than the relational one. Three common types matter. A key value store is the simplest, pairing a unique key with a data value, ideal for high-speed and very large data sets. A graph database stores data as nodes and the edges that connect them, perfect for networks like social connections or geography. A document store keeps richer, structured documents indexed by keys, often in common data interchange formats. Because their security models can differ sharply from relational databases, Learn the security features of whatever you use and design controls with your database team. Think of these as specialized filing systems, each shaped for a kind of data the classic table struggles to hold. So let's bring it together. Multi-level databases guard mixed classifications with trusted front ends and views, while concurrency locks data against lost updates and dirty reads. Aggregation and inference attacks assemble harmless facts into forbidden ones, countered by tight permissions, granular controls, partitioning, polyinstantiation, and noise. Connectivity layers let applications reach any database, and non-relational databases trade tables for key value, graph, and document models with their own security needs. Master these, and you can protect data even when every individual query looks perfectly legitimate. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 20.3. This is the 205th session of the CISSP Exam Prep series. In this session, we'll look past the database to the raw storage beneath it. We'll answer several questions. Why is database security not enough on its own? How do attackers reach storage without going through the front door? What extra danger does cloud storage introduce? And how can data leak through hidden storage channels? Why does this matter beyond the exam? Because a database can enforce every access rule perfectly and still be undone by the disk it sits on. Imagine a research firm that locks its application tightly but stores backups on a loosely configured drive. An intruder who never touches the application can simply read the files directly. Securing the front door means little if the back door hangs open, so protecting storage itself is where real defense either holds or fails. Why is database security not enough on its own? Because a database management system only guards the traditional front door channels, the queries and interfaces users are supposed to go through. The data itself still lives in the computer's storage resources, both memory and physical media, and those can be reached in other ways. You would never spend heavily to bolt the front door of your home and then leave the back door wide open. The same logic applies here. The underlying storage needs protection every bit as much as the query interface does. How do attackers reach storage without going through the front door? The most basic threat is illegitimate access to storage resources, and it exists no matter what kind of storage you use. If administrators fail to set proper file system access controls, an intruder can stumble onto sensitive data just by browsing the file system. In more sensitive settings, you must also guard against attackers who bypass operating system controls entirely and read the physical media directly. The strongest answer is an encrypted file system reachable only through the primary operating system. And in a multi-level environment, shared memory and storage need controls so that data at one classification level cannot be read from a lower level. Think of it as a locked filing cabinet inside a locked room. Even someone who slips past the room's door still meets a second barrier. What extra danger does cloud storage introduce? Storage access control errors turn especially dangerous in the cloud, where a single misconfiguration can expose sensitive data to the entire public internet in an instant. A storage bucket meant to be private can be flipped open with one careless setting, and suddenly anyone can browse it. So organizations using cloud storage should set strong default settings that restrict public access from the start, then watch closely for any change that would open that access up. Think of it as a vault whose door can be swung wide by a single toggle. You keep it shut by default and alarm any hand that reaches for the switch. How can data leak through hidden storage channels? The second major threat is the covert channel attack. A covert storage channel smuggles sensitive data between classification levels by directly or indirectly manipulating shared storage media. In its simplest form, this means writing secret data to a portion of memory or storage that is inadvertently shared. More sophisticated versions signal information by manipulating something indirect, like the amount of free space left on a disk or the size of a file, turning ordinary storage behavior into a secret code between security levels. Think of it as two prisoners tapping messages through a shared wall. Nothing obvious is passed, yet information still crosses a boundary it should never cross. So let's bring it together. Database controls guard only the front door, while the real data rests in memory and physical media that need protection of their own. Illegitimate access is countered with file system controls and encrypted storage, and multi-level environments must isolate shared memory across classification levels. Cloud storage raises the stakes, since one misconfiguration can expose everything, so you lock it down by default and monitor for change. And covert storage channels can leak data by manipulating shared space, a subtle threat worth remembering. Master these, and you protect data all the way down to the disk. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session. Welcome to section 20.4. This is the 206th session of the CISSP Exam Prep series. In this session, we'll explore systems that try to reason the way people do. We'll answer several questions. What is an expert system, and how does it decide? How does machine learning build knowledge from data? What are neural networks, and how do they learn? Where do these systems help in security, and how do you develop and run AI safely? Why does this matter beyond the exam? Because knowledge-based systems increasingly make or shape security decisions, and you need to judge whether to trust them. Picture a fraud team drowning in millions of daily transactions no human could review by hand. A well-built model can flag the suspicious few in seconds, but only if it was trained on sound data and secured against tampering. Understanding how these systems reason and where they can be poisoned is fast becoming core security knowledge rather than a specialty. What is an expert system, and how does it decide? An expert system tries to capture the accumulated wisdom of human experts and apply it consistently to future decisions, often outperforming people on routine calls. It has two core parts. The knowledge base holds the expert knowledge as a long series of if-then rules, like the guidance a seasoned advisor might follow. The inference engine reads those rules and reasons through them, using logic and fuzzy techniques to reach a conclusion for the situation a user describes. Its great strength is that it decides without emotion clouding the judgment, which is why lenders use such systems for credit choices rather than leaning on a loan officer's gut feeling about a likable applicant. Remember, though, that it is only as good as its rules and its reasoning. Think of it as a rule book paired with a referee who applies it the same way every time. How does machine learning build knowledge from data? Machine learning develops knowledge directly from datasets without a human spelling out every rule, letting the computer analyze data and refine its own models of activity. It falls into two broad categories. Supervised learning trains on labeled data, where the analyst supplies both the examples and the correct answers, so a model of malicious logins learns from login records already marked as good or bad. Unsupervised learning trains on unlabeled data, where no answers are given, and the algorithm groups similar items on its own, leaving an analyst to inspect the clusters and judge which might be malicious. Think of supervised learning as studying with an answer key, and unsupervised learning as sorting a pile of unlabeled photos into whatever natural groups emerge. What are neural networks, and how do they learn? A neural network chains together many computational units to loosely imitate how the human mind reasons. Where an expert system stores explicit rules, a neural network sets up long chains of small decisions that feed into each other and sum to a final output. Neural networks are a subset of machine learning, also known as deep learning, and they power tasks like voice and face recognition. They work in many layers of summation, each carrying weights that reflect how important a calculation is to the overall decision. Those weights are tuned during a training period, feeding the network inputs whose correct answers are known and working backward to set the weights, a process built on what is called the delta rule. Through it, the network learns from experience, though no network yet approaches the true reasoning power of the human mind. Think of it as a vast chain of tiny dials, each nudged during training until the whole chain produces the right answer. Where do these systems help in security? Knowledge-based techniques have real value in security precisely because they make rapid, consistent decisions. One of the hardest problems in the field is that human administrators simply cannot pore over the enormous volumes of log and audit data thoroughly enough to catch every anomaly. A system that never tires and applies the same criteria every time is a natural fit for that grind. Think of it as a tireless analyst reviewing every line of every log at machine speed, flagging the oddities a human would inevitably miss. How do you develop and run AI safely? As AI and machine learning become woven into software, secure AI guidelines from national cybersecurity authorities call for security across the entire AI lifecycle, built on a secure by design and secure by default mindset. It has 4 stages. Secure design treats security as a core requirement, with threat modeling tuned to machine learning risks like adversarial attacks and data poisoning. Secure development protects the AI supply chain, scrutinizing pre-trained models, third-party training data, and open-source components, and guarding the training pipeline and data integrity. Secure deployment ships with hardened, secure defaults, protecting the endpoints that serve models from theft and inversion attacks, and applying least privilege to interface access. And secure operation and maintenance monitors continuously for model drift, where accuracy degrades over time, and for live adversarial behavior, with incident response ready for AI-specific compromises. Think of it as the same disciplined lifecycle you apply to any critical software, extended to cover the unique ways an AI model can be corrupted. So let's bring it together. Expert systems pair a knowledge base of if-then rules with an inference engine that reasons without emotion. Machine learning builds models from data, supervised with labeled answers or unsupervised without them. And neural networks chain-weighted layers that learn through training. These systems shine in security by consistently sifting the log data no human could fully review. And securing AI means applying disciplined design, development, deployment, and operation across the whole life cycle. Master these, and you can both use and safeguard the reasoning systems reshaping our field. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.